It is not always as easy to estimate the parameter as it was to estimate the mean. Proceeding, we will examine how one can estimate the autocorrelation function, and this can actually be done in several different ways, with the two most common approaches being the so-called biased and the unbiased estimators. These are formed like this. This is the unbiased estimator, and this is the so-called biased estimator. As you can see, the estimators only differ in the used scaling factors, and at first glance it might seem quite surprising that why one would ever want to use the biased version. The summation is done over n minus k terms, so it seems a bit odd to scale with n, as is done in the biased version. And even if the name seems to indicate that the biased estimator is not what you would want to use, so it may be a bit surprising to learn that this is actually the estimator almost always used, and with good reason. Let's first examine the expected value of the estimator. As you can see, both of them are in fact biased, although the biased version is typically more biased. However, if you consider a zero mean process, the naming makes more sense. Then the unbiased estimator is indeed unbiased, whereas the biased estimator is still biased, although it is actually asymptotically unbiased. So why would one ever want to use the biased version? The answer lies in the variance of the estimator. The variance of the unbiased estimator will grow with increasing lags. You can see this by considering the extreme case. If you have n samples, the highest order lag that you can estimate is n minus 1, which is then formed by a single term like this. So the average is only a single component, which of course will yield you a very high variance. The biased estimator, on the other hand, will divide by n, independent of which lag it is, and the result will of course then get less and less accurate for the higher order lags. But since it is scaled by n, the actual value, and therefore the variance, will get smaller and smaller. This causes the variance over different lags to be roughly the same, which is much better than if it's growing. For this reason, we will always use the biased estimator. For a zero mean Gaussian process, one can show that the estimated autocorrelation function will have zero mean and variance 1 over n for lags greater than 0. Due to the normalization, the zeroth lag is always 1. But for higher order lags, which then should be 0, this is a quite useful result. That is to say, the mean will be 0, theoretically, but the variability will have a variance of 1 over n. It can also be shown that the autocorrelation function estimates will also be Gaussian distributed. This means that we can form the 95% confidence interval as plus minus 2 over square root over n. Here we use 2 in place of 1.96 as all of these results are only holding asymptotically, so it makes very little sense to use 1.96. Their results are simply not as accurate as that. This means that if we estimated the autocorrelation function, we have a way to determine if the estimates are statistically significantly different from 0 or not. That is, if the estimated autocorrelation function are within the plus minus 2 over square root over n, they are not statistically significantly different from 0, and we can conclude that the process is white. Note that this assumes that also the autocorrelation function is Gaussian, so we want to examine if this is a reasonable assumption. Otherwise, we cannot actually rely on the confidence interval we have derived. It's also worth noting that we can allow 1 in 20 to be just a little outside the confidence interval, as it is the 95% confidence interval. Another thing to be aware of is that the rule of thumb saying that you should not estimate correlations higher than n over 4. At higher lag, it's not uncommon that strange correlations will appear, suggesting that there are longer dependencies in the data, but these are most likely then just finite data effects and are spurious, and so you should not trust or estimate these. We will in the following strive to build a model for the data that we have observed, and then we will filter our measurement through the inverse of this model to see if the residual, that is the part of the model that has not been able to explain, if that part is white. If it is, then the residual contains no further structure that we can exploit and we are done. However, if the residual is not white, we can perhaps improve our model further by exploiting these remaining dependencies, making the model better. We will return to this in the following.